Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Welcome back. Problem 5.14. The statement is that assuming that reaction of ground is uniformly distributed, draw shear and bending moment diagram for the beam AB and determine maximum absolute value of shear and bending moment. So you can see this beam and the ground is exerting uniformly distributed load. So it is being given that you have to draw the shear force and bending moment diagram and then find the absolute maximum value of shear and bending. So let's start with the solution. So for that we will draw the free body diagram. So you can see if this is the beam, and if we remove this ground support, so it will be replaced by a uniform distributed load which will be represented by W. So I have drawn it over here. This is W and this load is represented as W, clear, and it is acting on a length of 12 feet, clear. So what we have to, we do not know this W, so first of all we will find this W by using the equilibrium condition, that is sum of all forces along y direction must be equal to 0 and taking upward force as positive. So from this figure you can see this is uniformly distributed load, this is 2 kips per feet distributed load, this is distributed load, and this is point load. So we will convert this distributed load, this load and this distributed load into a point load. So how we will do this? So again you can see this is a distributed load when this is acting on a length of 3 feet. So when you multiply this distributed load, which is 2 kips per feet, with this length 3, it will be converted into point load. The second force, and since this is downward, so it will be negative. Similarly for this force, it will be again minus 2 into the length over which it is acting is 3 feet. So 2 into 3. Another load is 24 kips, which is acting downward, so minus 24. And the fourth load is positive load, which is upward, and this is W into total length is 12 feet. So 12 into W, and their sum must be equal to 0. So when you solve this, you will get distributed load W is equal to 3 kips per feet. So this is the value of uniformly distributed load that grounds act on this beam. Now for finding the shear force and bending moment at each section, we will section the beam at various locations. So first we will section beam at this point. This section is 1 from A to C. So from A to C, means that x is greater or equal to 0 and less or equal to 3 feet. So when you section the beam, I will draw it and will draw the free body diagram. So this is beam, clear. This is distributed load of 2 kips. I will write it over here, 2 kips per feet, clear. And in downward you have distributed load W, and this distance is taken as x, and x start from 0 and less than 3 feet. So when you cut the beam at location 1 1, clear, so definitely there will be a shear force V and there will be external moment M, and let this point where we section the beam is J, clear. So for finding the shear force, we will apply equation sum of all forces along y direction is 0 and taking upward force is positive. Now you can see this load, it was W, and this W is 3 feet, kips per feet. So one force is this force, which is 2 kips, and it is acting over a distance of x, not 3 feet, because this is x distance. So 2 into x will convert this force distributed load into point load, and that will be minus, plus 3 into this distance, plus 3 into this distance x will convert this distributed load into concentrated load or point load, and it will be acting upward, minus this v is equal to 0. So from here we will get 3x minus 2x will be equal to x. So v is equal to x, and the unit will be equal to kips. This is our equation number 1. Now for finding the moment, we will take sum of all moment about point J is equal to 0, and taking the counterclockwise moment as positive. So moment about point J is the first force, which is 2 into x here, and this 2 into x will acting at the mid of this x. It will acting at this. So the remaining distance is x by 2. So 2 into x by 2. And it is producing counterclockwise movement, so it will be positive. The second force which is producing movement about point J is this 3 kips per feet. So you have to convert this 3 kips into force. So 3 into x, and again it will be acting at the mid. So this distance is x by 2, and it is producing clockwise movement, so it will be negative. So 3 into x by 2, plus this external movement which is counterclockwise. Their sum must be equal to 0. Again, when you solve this, you will get the moment is equal to 0.5 times x square, and the unit will be equal to kips into feet. So this is equation number 2. Now this equation 1 and 2 is valid for x is greater than 0 and less or equal to 3 feet. So let's put if x is equal to 0, so shear force will be 0, and if x is equal to 0, we will get shear force is equal to 0 and bending moment is equal to 0. Now for x is equal to 3 feet, for x is equal to 3 feet, or we can say at c minus, or you can see at c, okay, c, clear, at c, this is c point, clear. So for x is equal to 3 feet, you can put it over here, so v will be equal to 3, clear, kips, and movement will be equal to 0.5 into 3. So 3 square is 9, and when it is multiplied by 0.45, it will be equal to 4.5. So 4.5 kips into feet. Okay. Now we will section the beam at this 2, 2, clear, and 2, 2 means that x is greater than or equal to 3 feet and less or equal to 6 feet, or from C to D. So from C to D means x is greater than or equal to 3 feet and less or equal to 6 feet. So when you cut the beam over here, so definitely you have to draw the free body diagram. So I will draw it over here. So it will be like this. The upper 2 feet, 2 kips per feet will be there over the length of 3 feet. So it is 2 kips per feet, and this length is from this to this length is 3 feet there, and below you have distributed load of 3 kips per feet. This is 3 kips per feet, and we have taken arbitrary distance x, and x is greater than or equal to 3 and less or equal to 6 feet. So this distance is 3 feet. Okay. So when you cut the beam, there will be a shear force and a reaction moment. So let this point is J. Now we will find the equation of shear force for this. So sum of all forces along y direction must be equal to 0 and taking upward force as positive. So this distributed load 2 into 3 will be converted into vertical force, and this is downward, so it will be minus, plus 3 into this distance will give you point load here, and minus V, their sum must be equal to 0. So when you solve this, you will get this shear force is equal to 3 into x minus 6 kips. The unit will be kips. Let this is equation number 4. Now moment about point J, sum of all moment about point J must be equal to 0 and taking the counterclockwise moment as positive. So you can see the first force that is producing moment about point J is this distributed load, and we will convert this distributed load into concentrated load. So 2 into this distance is 3, which is equal to 6, and it will be acting at the mid of this clear. So mid of this is 1.5 clear. So remaining distance will be equal to x minus 1.5. Okay, or 3 divided by 2 will give you 1.5. Okay, so this force into perpendicular distance is x minus 1.5, and it is producing counterclockwise movement, so it will be positive. The other force which is producing movement is this 3 into x, and it will be acting at a distance of x by 2, because it will be acting at the mid of x, so remaining will be x by 2, and this is producing clockwise movement, so it will be negative, plus this external movement, their sum must be equal to 0. So again from this you will get the equation of moment is equal to 1.5 x square minus 6x plus 9. This is the equation of moment, and the unit will be kips into feet. And this is your equation number 4. Now at D minus, now what does it mean at D minus our x is equal to 6 feet? So you can see that at point D there is a point load as well. So just before point D we consider that at x is equal to 6, when you put x is equal to 6 in this equation, so you will get V is equal to 12 kips. 12 kips. Okay. Because 3 into 6, which is 18, minus 6, 12 kips. Clear? And moment at x is equal to 6, so you have to replace all x with 6, so you will get moment is equal to 27 kips into feet. But now you know that exactly at x is equal to 6 there is a load of 24 which is downward, so the shear force will change from 12 to minus 12, because 12 is acting just before point D, but at point D there is 24, so 12 minus 24 will be equal to minus 12. Or you can also section it at 0.3, and you can apply the same method to find the shear force at x is greater than or equal to 6 and less or equal to 9, and you will know that the shear force will be minus 12. Okay, similarly now you can see that we have covered this up till this equation, section 1 and 2. So the load, you can calculate the load over here as well, and you will find that this load will be in symmetry. Using symmetry you can evaluate the load over here, shear force over here, and bending moment. It will be the same as we calculated over here, but the sign will change. Now let's move and draw our first part, that is to draw the shear force and bending moment diagram. So again I have to draw first the shear force, so I will draw it over here. For drawing shear force, I will take a horizontal axis which will show the length. So here we will draw the shear force, that unit will be equal to kips. Let each division is equal to let one division is equal to 1.5 kips. So 2 division will be equal to 3 kips, and 12 division will be equal to 12 into 1.5, which will be equal to 12 into 1.5, which is equal to 18 division. So 18 division I will not be able to draw it, so I have to change the scale for that. What I have to do is I have to move this axis somewhat below. Okay. Now you can take here one division is equal to 1. There 1 kips. So at x is equal to 0, we know that we have shear force is equal to 0 and bending moment will be equal to 0. So it will be 0. And here 1 division is equal to 1 feet. Clear? So at x is equal to 3, we have v is equal to 3 feet positive. So 1, 2, 3. So it will be like this. So this is 3 kips. Clear? Similarly, at x is equal to d at this point, 1, 2, 3 at this point, we know that at x is equal to 6, we have v is equal to 12. So we will plot 12. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is 12. But again at point D, this is point D. Clear? This is 12. But here you can see that there is 24 kips downward. So 12 minus 24 will change the shear force to minus 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it will be minus 12. And again, this at a distance of 9 feet, it will be minus 3, because this is in symmetry, but sign will change. And at end, the force will be 0. Now you can join them and you can get the shear force diagram. Join it by using different line. Here you have to draw it by using ruler. this will be -3, and at the end it will be 0. So this is your shear force diagram. I will mention the value here. The shear force is -12, here is 12, here it will be -3 kips, and here it will be 0. So this is your shear force diagram. Now we will move toward bending moment diagram. So for bending moment, again what I have to do is that I have to extend it below. Similarly, I have to extend the legs and we will draw a horizontal line. So here we will draw the movement. Okay, we'll draw the movement that will be in kips into feet. So let one box is equal to one division is equal to vertical is equal to 2 kips into feet. So definitely at x is equal to 0, movement will be equal to 0, and at x is equal to 3 we have movement is equal to 4.5. So 1, it will be 2, 2.5, it will be somewhere here. At x is equal to 6, at the mid we have movement is equal to 27. So I will go 12 division above, which will be 24. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 24, 26, 27 will be somewhat here. So this is 27 kips into feet. This is 4.5. So what you can see that shear force is, all the slopes of shear force are positive, moving upward here. So bending moment will be a second degree and it will be counterclockwise. You have to join them. You have to join them like this here, and similarly here again at a distance of 9 feet it will be 4.5. So it will be same, it will be moved toward, it will counterclockwise. You have to draw the curve. I'm trying my best, but it is second degree curve and it will be counterclockwise, and again same, it will be counterclockwise and it will be equal to 0. So from here you can see that from shear force diagram, if I move it a little bit above, so here you can see the maximum shear force mod is equal to 12 kips, while maximum bending moment absolute value is 27 kips into feet. So these are the answers of our problem 15.4. I hope you have enjoyed the video. I will advise you to solve some problem by using proper scale, and I hope that you will be able to draw such type of shear force and bending moment diagram. Thank you for watching and supporting me.